Yeah, thanks a lot, Sergej, for the introduction, and also to both of you, Sergej and Subhro, for putting together this nice workshop. It's really great to be here. Enjoy it very much. So today I'd like to cover actually some applications of what Julien has told us before. So I'd like to show you how one can probe some exotic phases with topological order and anyonic excitations on quantum processors. So this work has been done in collaboration with a bunch of people. So the top row are the Munich crowd, so our PhD students and also former ones, Leo, Julian, Bernhard, and Melissa. So Leo is now postdoc at MIT. Wentao and Adam has been postdoc in our group. Wentao is postdoc in our group. And all of this has been done in collaboration with my colleague, Frank Bollmann. And I will show you a couple of experimental realizations of topological order. And so these are applications which we did together with Google Quantum AI, with these folks here. Good. So, you know, matter we experience to occur in different phases. So, for instance, when we take water, it can be either in its liquid form or in its solid form, depending on temperature. And such phases of matter, as we know, can be characterized quite simply by spontaneous symmetry breaking and by local order parameters. So, when you take, for instance, ice, or a lattice structure, then when we just look locally, we can tell who are my neighbors, and translation and rotational symmetry is spontaneously broken, whereas in liquid, it's not. So we have full rotation and translational symmetry. And then we have seen today examples of states of matter which actually do not order at the lowest temperatures. And you know, I think the first idea, at least, where these kind of states of matter have been put forward was actually by Phil Anderson. He wrote a paper in '73, so now more than 50 years ago, so before the notion of anyons and stuff like this, about resonance-valence bond states. So these states of matter are basically singlet coverings on a lattice which form a massive superposition and have very peculiar entanglement patterns and also excitations. And they have an underlying topological order. So, you know, understanding topological order, we made a lot of progress by knowing analytically solvable or exactly solvable models. For instance, those by Kitaev, so Kitaev honeycomb model, or the Tori code, or more generally, all the string net states in 2 dimensions, for instance. So this taught us a lot about how to think about topological order more from the practical level. Let's put it like this. When we want to depart from these kind of fixed point states, as we call them, then we need to use numerical tools to study those systems. But we also know, you know, that the Hilbert space is growing exponentially with the number of particles which we add to the system. So I know when then we maybe are limited at something like 40, 50 spins, which you can exactly diagonalize. And then there are, of course, sophisticated methods like tensor network methods, which can help us to go beyond these space limitations, but they are limited by entanglement then instead. So a question is whether there are other tools than these traditional tools to actually study topological order, and maybe also in what way can we do that. And what I'd like to cover today is actually I'd like to advocate that maybe we can use quantum processors as a new computational tool to study these types of matter. So this is the main overarching question of this presentation of today, and I will cover, let's say, sequentially a couple of steps with increasing complexity in some sense. So first, I will show you how one can actually realize simple topologically ordered ground states on quantum processors. So here in particular, we will focus on the Tori code, and I will show you how one actually can characterize now or do experimentally what we have just seen mathematically in the previous lecture, how we can do this on a device to do the anion braiding, or let's say ask about properties of fused particles and so on. In the second part, actually, I will go beyond these fixed point limits and try to put in correlations to these states and try to look at emergent phenomena which we have in such systems. For instance, you can have, when you switch on fields, a mechanism of confinement of anions, and there you have strings connecting these anions, and the question is actually what is the dynamics of these strings? So this will be a dynamics on top of the ground state, which is even more complicated to handle numerically at this point. And the third example will be a topological order which does not which cannot exist in equilibrium. It's a genuine non-equilibrium form of topological order, and we call it Floquet topological order. It also has other names in the literature, but I will explain to you as we go through this presentation what I actually mean here. Good. So let's start with a simple example for topological order and fractionalization, which is the toric code model introduced by Kitaev. So we have seen it already a couple of times in this lecture, and Vijay has given a nice overview. Let me nonetheless set the stage and also my notation for this model here again. So we have a model which lives on the square lattice. The qubits are sitting on the links of the square lattice, and the Hamiltonian only has two terms. One term is the star operator, which is a product of four C operators in my notation. So that's flipped compared to the convention in literature. So it would be C1, C2, C3, C4. So these are the star operators. And the second operator are the plaquette operators. These are products over X's. So it turns out that these two operators are mutually commuting because, you know, we have always two Pauli operators shared between these two operators. So 2 times anticommutation is commutation. So this means that we have this hierarchy here where each term of the Hamiltonian is commuting, and this makes the model exactly solvable because actually the elements of the Hamiltonian are so-called stabilizers, which are also eigenstates essentially, where the ground state or all the states in this model actually are eigenstates of these stabilizers. So the vertex operator, a vertex on the toric code just gives back the toric code state, and the plaquette operator as well. This is because of the sign convention which we have in Kitaev's model. Good. So, you know, what do these terms do? When we think about the spin configurations, in order to fulfill the stabilizers here, the C stabilizers, what we need to do is we need to have an even number of spins flipped at each vertex, because only then the product of them can be positive. So what are the options which we have? Well, it could be something like or maybe let me go to the next slide to really introduce the wave function a little bit here. So here I introduce a notion, again, I show on you on a lattice, the this is like a Fock space representation of my state. So I just show you graphically how the Fock state looks like, with the eigenstates of the local C operator being +1 whenever there is a red line, or -1 whenever there is a no line. Okay? So in this representation, what the star operator wants is actually to have an even number of lines intersecting at each cross, because then I will get positive signs for the stabilizer. So now I have only a couple of options. So the options are that there is nothing, like here, that's good. The other option is that there are 4 loops entering, so I have a full vertex, or I have a corner like this, or I go through straight. These are all the options which I have for making the stabilizers A nu happy. But at the same time, we also want to have an eigenstate of the plaquette operators. In order to achieve that, we have to have a massive superposition of states, right? Because each plaquette operator actually flips, let's say, a plaquette from 0 or from black to red. So it makes just a loop bigger. So in order to be an eigenstate, I have also to have the conjugate configuration with a bigger loop, which is then reduced by the application of the plaquette operator to a smaller loop. So in other words, this state of topological order is just a massive superposition of loops, a loop soup, which is created by just applying 1 plus the plaquette operator on the vacuum state. So I get no loop, 1 loop, like multiple loops, bigger loops, smaller loops, and so on. And this massive superposition encodes this quantum spin liquid. It does not have any traditional symmetry breaking. Tomorrow I will tell you more about the higher form symmetries in this model and how we understand that. But today let's keep it just simple. So we have no conventional symmetry breaking here, but topological order instead. And the type of topological order which this toric code model has is actually Z2 topological order, because the parity of loops is conserved. So when you make a cut here, we see that the parity of the loops is always 0 in this state of matter. Good. Well, there is some hidden structure in this topologically ordered state, which is that we have fractionalized excitations and non-local entanglement. The fractionalized excitations we can create, for instance, by acting with an X string on the primal lattice of the system. So this would be a string like this, which flips my spins. And then you see at the ends of my string, the vertex operators will be unhappy. So there is then only, let's say here, 3 empty and 1 full configuration. So this is not fulfilling essentially the ground state rule, but it's rather creating an excitation in the system. And these excitations are deconfined. Once they're created, we can move them apart without any additional energy cost. Good. The question now is, how can we represent such a state of matter on a quantum computer? So it's a massive superposition of states. And in order to do so, we just need some elementary operations. These elementary operations are just 2. One of them is a Hadamard gate, which basically makes a pi/2 rotation to a spin. So it creates a superposition from a 0 state to a 0 + 1 state, like this. And the second one is a gate which creates entanglement, which is a C0 gate. The C0 gate is also very simple. So when the input is 0, then the output will be 0. And when the input is 1, then the output is 1. There are also 2 other configurations which I don't need. But the point is, it's a bit like drawing loops, because whenever there is a 1, it will continue to be a 1. Whenever there is a 0, it will continue to be a 0. So that's the role of the C0. Good. With these 2 elementary contributions, we actually can already write down the quantum algorithm which creates the toric code ground state. So it's very simple. It basically, so what we want is this massive superposition of plaquettes. So how do we do it? Well, this is our qubit grid, if you want. Whenever you have these zeros here, this is where the qubit sits. So this is just, at the edges of my lattice as I want to have it for the toric code. And what I do first is I apply a bunch of Hadamard gates, which initializes these superpositions, which I want to have ultimately. Then I draw in a sequential way C0 gates, which are just drawing my loops and connecting them in a proper way, so that in the end, after a sequence whose length depends on the system size, I will create the toric code ground state. And this is now indeed experimental data, which we did together with Google a couple of years back, where you see how the stabilizers are measured after each step of the preparation protocol. First, with all zeros, the stars are happy. The stars are always sitting, at the crosses here of the plaquettes, because all of them are fulfilled, right? No lines, they are fulfilled, but the plaquettes are all unhappy, so none of them is properly in 1. But after sequentially going through, we will see that we zip out from inside to outside this topological ordered state here. What we need is, so this toric code fixed point is here generated sequentially. We need a circuit which is in linear in depth in the system size Ly in order to build up this topological order. Another way of creating such a stabilizer state is actually by doing measurements and prepare it by measurements. Then you can do it in one shot. But here, I like somehow the sequential preparation, and I will tell you a bit more about it. The reason is because the intuition behind it is actually a tensor network representation of the toric code. And we directly map a certain subclass of tensor network states, which we call isometric tensor network states, on the quantum computer. And this is much more general than doing a fixed point measurement. So the point is we can do parallel operations. We can do every row in one shot and then zip the topological, or maybe let's... Okay, maybe let's first do a simpler geometry, which is more the tensor network way of thinking about it. Let's start in a corner, and then I can go diagonally through the system sequentially. This also will be linear in system size times square root 2, doesn't matter. Our rotation is a bit more optimal. Then we lose the square root of 2, and we get it linear in Ly. This is just an optimal choice of how I go through the system. But this makes sense, not that I start at the beginning and then I just zip through and create my topological order in that way. And of course, in a quantum computer, I can apply gates in parallel. Also here, I create with a massive superposition in the beginning already with all my Hadamars. And then I apply the C-naughts to draw in parallel all my loops in some sense, right? So that's how by standard quantum parallelism, essentially, we can apply it in that way.
Am I correct that the total number of C-naught does go like
Yeah, right. So this, it has to be entangled here, but the question is how deep, well, it depends on how you count. How deep is a circuit? Usually we count in terms of layers because this is preparation time, but this is maybe a matter of convention. Very good. Yeah, please ask questions all the time. Let's just see. Yeah, Sergej. No, I mean, how, okay, sorry, maybe I was very fast in how I explained this. So this is first step, second step, third, fourth, fifth, sixth, seventh, right? The sequential part is like, this is first part of the sequential, second part of the sequential, third part of the sequential, fourth, and fifth. All one picture is done in parallel on the quantum processor because these are all non-overlapping C-naughts. By the length of these pictures. Because at each time I apply basically C-naughts in parallel on a certain subset of qubits. This is how we count depth. Okay. Yeah, so how you can see that is, so we measure after each preparation, we measure the stabilizers. So the stars, which are sitting here, and we measure the plaquettes. And you know, first the stars are all happy because we are all empty, and this means we have all the zero crosses. These are eigenstates of my star operator, they are fulfilled. But the plaquette operators are not fulfilled because if I measure them, I just rotate everything. It doesn't work. There's no partner to rotate into. When I apply the Hadamars, then I also mess up all my set stabilizers because I made superpositions. There's no one is happy. But then I can start zipping in essentially this topological order structure from inside to outside. And with that, we create basically this entanglement pattern.
At no point do you need decoding.
No. This is a sequential circuit. There's no decoding, no measurement and error correction, right? So measurement would be another way of creating stabilizers. But my point is, in this way, I have a quantum algorithm which creates a toric code. And you know, the background of this is actually that there is an isometric tensor network state which has a certain form which amends to writing down this toric code. I can give you more details if you're interested in this. But the point is, you know, I can easily amend this isometric tensor network state to build, for instance, a finite correlation state. And this is not possible with measurements and feedback easily. Then I would have to do measurements first and then apply a certain sequential circuit afterwards. So it will be a two-step process. Here I can get it in one shot with finite correlation length, for instance. So that's the advantage. And I will show you a bit of examples later, maybe, in this direction. But these are two parallel ways of preparing this type of state, right? There's not one is better than the other. Okay, very well. Good. So with that, you know, we have already measured the stabilizers. We are purple and blue. Looks all quite good that we have the proper state realized. But now we actually probe the intrinsic properties of this quantum spin liquid what we have. But first, maybe before we do that, let's just look at numbers. How well are actually the stabilizers really fulfilled in this device? And this was already in, so the measurements were done in 2020. Back then, right, so back then on the Sycamore device. And so the fidelities, what we had was about 90% for each of these stabilizers, right? So which you can create. Okay, I mean, the question is, I mean, is this now good or bad? Let's see, I mean, how many of the properties of the toric code are actually governed by this quantum state of matter, which we have created in this sequential circuit. And you know, just in a pictorial way of what we have seen before, the properties which we want to measure, maybe here are the properties of the anionic excitations. So on the one hand, we want to study the exchange statistics of these anions. And on the other hand, we also want to study the mutual statistics of the anions by just taking anion A and B and and turn A around B, essentially. So for this, there's no analog for anything like fermions or bosons in 3 dimensions, right? And the exchange statistics for anyons could take phases other than plus minus 1 in principle, as we have seen before, or hinted at before in Julien's talk. So how do we do this actually in the lab? So what we want is we want to create anyons, and we know that we can create anyons only in pairs. So this we do in that way that we actually create strings of anyons and we move them into the center and leave the other anyon somewhere outside at my state. So now I have 2 anyons, an E and an M anyon, in the center of the system. And in the Tori code we have seen before, we have 4 types of anyons: the identity, the E, the M particle, and the fusion of the E and the M, which is the epsilon particle, or we call it psi particle in our paper. So first we just look at the statistics of the E and M particle, and what we literally want, and this is also experimental data, is now to apply an X string which moves the E particle around the M particle and then measure a phase. So how do you measure a phase? A phase is a property of a wave function, which usually is not accessible, as we say, right? Because we can always shift energy, and phase is anything. But here, of course, we may have to measure a relative phase, which is accumulated during this process of moving the E particle around the M particle. So this process can be done simply by a Hadamard test. A Hadamard test uses an ancillar qubit which conditions my wave function to a wave function where nothing happens if the ancillar qubit is 0, to a wave function where the braiding happens when the ancillar is 1. This is illustrated by this process. So if the ancillar is 0, then I don't do anything to the E and the M particle. If the ancillar is in 1, then we do a braiding process of the E and the M particle. Now I can easily write off the relative phase accumulation in this process, because it's just the relative phase between my interferometer, where I do nothing, and where I do the braiding. So that I can literally read off by just measuring Pauli operations on my ancillar qubit. Because it's just a phase, I can map it out by a single qubit measurement. And this is what we do. So we stick an ancillar qubit somewhere out here, condition the braiding on this ancillar qubit, and then do all sorts of braidings which we can have in this simple theory. So we can have all the mutual statistics. So we have, let's say, or maybe let's do the exchange first. So we see basically here we have the exchange of an E particle, gives me a phase of 0. So it would be bosonic if you want, M particle also, and psi. And that's the surprise here in the series. So the composite of the E and the M is actually fermionic. And that's somehow the surprise of this topological order, if you want, because even though I started out with a completely bosonic theory, the entanglement pattern in my background are arranged in such a way that these composite objects of E and M, they actually become a fermion. So they are not bosons anymore. And here, literally, what we did is what Julien told us before. So we just put together, we fuse E and M, we put them together like this and move one particle around the other in order to get this phase of -1.
So I suppose the key part of how to do this is actually, you haven't told us what game, but suppose it's written that and all that.
Yes.
You need to do something special to make that happen.
Yes, in order to condition this, we need to condition the excitation on the ancillar. So we need to have a control operation on the creation of the excitation. And then the control operation then depends on which type of anyon I have to create. But this is easy in some sense, right? So it's a multi-control. No. We first have to condition. This is just for which type of particle I want to create. For instance, the M particle here, and then I have already conditioned those two. Now I can do the manipulation because this is conditioned on this creation. You're right. No, you're right. I mean, basically, the whole path is conditioned on the ancillar qubit. But that's still possible. It's a few body control project. So object. So what we do is actually also we do the smallest possible path to do the braiding. So when I go away from the fixed point, this will be much more complicated. So here I have 0 correlation length state, and it's relatively easy to go around. And when I have a large correlation length, I would have to go a large path, then it's much more complicated.
But again, more engineering
Mm-hmm. Well, this is in one shot in some sense, right? Because this x, which I showed you before, we can also do it with one application of a string of x. And this is what I have to condition my ancillar qubit on, right? As one layer, this is one layer then controlled on the, either I braid or I do not braid. Very good.
Sorry,
yeah, sure.
In Sycamore, is a sense of geometry. What determines what?
Yeah, I mean, in Sycamore, it's actually perfect. And I guess it was also designed like this. It has the structure of the toric code. So, oh, and continuum is also easy because continuum would be a trapped ion, a reconfigurable quantum processor where you can basically put everything together. It has all-to-all connectivity. Because, you know, they bring basically ions into the entangling zone, do entangling, bring them out again in the storage zone and back and forth. So there's not even a restriction to geometry. You can also do 3 dimensions, for instance, or periodic boundary conditions, as we've shown in another application. So superconducting qubits in that sense are more rigid because you have to work with the underlying geometry, which we have here. But the toric code is perfect because they have this type of structure for the couplers, because the couplers are kind of oriented in that way. Good, but that's very nice because we get the full statistics, essentially onion statistics of our topological field theory, of the Z2 topological field theory realized in this Z2 toric code fixed point state, essentially. Okay, good. Now, next step is related to the total quantum dimension, which we have seen already before. You know, we can also measure the topological entanglement entropy, which is a part in the entropy which goes beyond the area law. So you always have an area law contribution and then a topological entropy contribution for states with topological order. And it turns out that the topological entanglement entropy is actually given by minus the logarithm of the total quantum dimension. So now we can readily apply the formula which we have seen before. So it was just the sum over, so we just saw that the total quantum dimension was the square root of the sum over dA squared over all A. We have abelian particles, so dA is 1. We have 4 species, so it will be sum over 4 ones. So we get square root of 4, which is 2. So for the toric code, we would expect a topological entropy of minus log 2. So we can measure this in a geometric way by getting rid of the area law contributions. So this was what Kedaev and Breskill, and in parallel also Levin and Venn have proposed, that we can measure actually the topological entropy by doing this, for instance, is one choice of the geometry, by doing these tripartitions in areas A, B, and C. So what happens when you do this is that you can basically count the entropies of the individual parts plus the entropy of the total part and subtract the entropies of the A-B subsystems. With that, you basically get rid of all area law contributions. You can do the counting geometrically. These guys have wedges, essentially, in the same wedges appear here, they are cancelled, but we get in addition another total circumference, which is cancelled by this one. Right? So this is how you do the counting here. And so in that way, all what is remaining is the non-area law contribution to the topological entanglement entropy. And this is actually, should be, by the information which we got before, log 2. And now, how do we do that? I mean, in order to measure that, you need to do tomography. Or you can do randomized measurements, shadow type ideas. So you can do tomography up to systems of 6 qubits, and we get a topological entanglement entropy, which is 0.9 roughly. You can also do it for the little bit larger system, and there we need to do these randomized measurements essentially to really estimate the entropy at the toolbox which has been developed by Breskill and company. So, and there we get, well, even a little bit better entanglement entropy of 0.95, close to the log 2, which we use here. We use the units of log 2. So -1 would be the ideal situation which we have. So the entanglement of this quantum state we've created is also compatible with the toric code state. And I mean, I don't know, I mean, it's getting a little bit better as we increase the system size. So could be coincidence, or maybe it's indeed that there are some, because of errors, that there are some local correlation lengths which we are forming, which are basically a bit cancelled out by going to larger geometries. Because of course, if I'm not at a fixed point, the geometry which I need to capture this log 2 has to be large, because it has to be larger than the correlation length in my system. Mm-hmm.
Since not everybody in the room is an expert, can you define what is the model?
Okay.
Actually, what is exactly the model?
Right, so what you need to do, of course, I mean, entanglement entropy is minus rho log rho, right? So for Neumann, entanglement entropy would be minus rho log rho. Rho. And the point is here, for these stabilizer states, what we can actually do is, in order to measure the entanglement entropy or the Rényi entropies, which are basically, let's say, powers of the density matrix, give the same topological entanglement entropy, because the entanglement spectrum is flat, essentially. So what we measure actually is the logarithm of rho squared. So rho squared is the entropy which is the Rényi entropy, the easiest one to measure. But what we need in order to get rho squared of a subsystem, we need to have the reduced density matrix of the subsystem. So how do you get that? You need to somehow build up this density matrix. And the simplest way of doing it is just to measure all Pauli strings in the sub. No, inside, because it's inside, right? Because outside, it's a complement, it's the same thing. So we need to measure this, and then we get the reduced density matrix. From the reduced density matrix, we can determine the entanglement entropy.
Just to be clear, this is not measurement.
No, this is measurement. This is many measurements, and then, of course, afterwards, we need to reconstruct the density matrix and then do the processing to obtain the entropy, essentially. And this is actually also quite non-trivial. I mean, there are many pages which may explain in this paper how we do it concretely. Right, so this is 2 cross 2 would be this subsystem, 2 cross 3 would be this subsystem, and 3 cross 3 would be this subsystem. And the bottleneck is, of course, always to measure this guy, right, the biggest one, which is then the 9 qubits. Say again? Fixed point of the toric code. Oh, no, what I mean with this is, for topologically ordered states, we can write down, let's say, 0 correlation length states, like the toric code. It doesn't have any correlation length. It's a stabilizer state. We can write it down just as a solution of this Hamiltonian, which I showed you before. Now, topological order is robust to certain types of perturbation. So topological order is robust, for instance, when I apply a little bit of a field to the system. Then, however, I depart from the fixed point and I get a finite correlation length. So in that sense, when I talk about fixed points, I mean the 0 correlation length point in this topologically ordered phase. And for all the string nets states, which we have heard before, we can write down these fixed points very easily. They are geometric objects like superposition of loops, maybe loops with different colors, but those can be easily written down, and they don't have any correlation length. This is why a fixed point. The topological field theory would be a coarse-grained view of this lattice model, essentially, right? That's the idea. So it would be basically, if I coarse-grain, then I can write down fields, and I can write down, I don't know, Chern-Simons theories, which has anions, which has the same properties as the topological order, which I want to describe here in this system. But I'm thinking more about minimalistic models, according to Occam's razor, if you want, which capture this topological order. Okay, this is my approach here. It's a lattice model approach to topological order. Good. And maybe out of curiosity, we can also take such a toric code, and we have seen that on a torus, it would have a 4-fold degeneracy because of the Wilson loops, which you can span around in either way of the torus. In open boundary conditions, the ground state is unique. However, it is a bit more tricky, as we have also seen in the Vijay's lecture on Monday. It can also be in such a way that the ground state is degenerate, depending on how I determine my surface. And then these type of states go under the name of surface codes, and here is a particular boundary condition shown where actually the ground state is two-fold degenerate, and in that way we could really use this two-fold degenerate ground state to encode a logical qubit in this toric code. So basically here this is a block sphere which we wrote with states prepared in the logical state of the surface code of the toric code. Okay, so that's the first step. This is not error correction or anything, right? So it's just preparation. Take the two-fold degenerate ground state manifold and make superpositions out of them. Yes? Yes, after every measurement. So this is destructive. So the question was whether in the tomography we have to do prepare the state many, many times, and the answer is yes. So it's a destructive measurement. Each time we measure, I have to start anew and run the experiments. These are actually data where we took about 1 million measurements or something like this to actually reconstruct this density matrix. Oh, sorry. Yeah, I know, I did. Again? Oh, the measurements are very fast. The measurements are hours, I would say. I mean, now it depends. There are many different experiments. Now the question is for which experiment, because the cycle times are actually, okay, so now maybe I should, I don't remember it very precisely, but I think it's on the level of microseconds. So 1 cycle. So then you can. Good. Okay, so this is how one can think about these states and how one can prepare them on quantum processes. Now the question which we should ask ourselves, well, is this a singular example which we can prepare, or is there more structure behind it? Is there a more general recipe of writing states with topological order or writing quantum algorithms for states with topological order? And it turns out that, you know, the structure of these abelian string nets and also non-abelian string nets actually is very nice. It is in such a way that we can write down tensor network states which have an additional condition, which is the so-called isometry. I don't go into the details here today, but all of those states can be directly translated to unitaries, and therefore we can have a quantum algorithm which writes all the fixed points of the string nets. A subclass would be the abelian string nets, which are looking like this. So these are very similar to the toric code, which I showed you before, but now I have strings with colors, okay? And they're a bit more complicated, maybe how they're patched together. And there it turns out that all of these states can be easily prepared on the quantum processor, first of all, but there's more to it. You know, we can now, and this was work actually by Julian, who's sitting here in the back, so we can now deform these fixed points in such a way that we build a skeleton connecting different types of topological order. So for instance, we can, I don't know, start out with the Z4 toric code, go to 2 copies of the Z2 toric code, maybe go to a Z2 double semyon topological order or double semyon, 2 copies of the double semyon, and all of them are connected via critical points. These critical points are the red dots in this web of or skeleton, if you want, and the faces are the colors, essentially. And this parametrization, so the fixed points are the bullets here, and those correspond to the zero correlation length states. Now, when I depart from those, I actually get a diverging correlation length, which becomes a power law at the critical point, and then it becomes exponentially again when I depart from it. Okay? In that way, we have somehow a simple organizing principle, if you want, for abelian string nets by just using this kind of web, which we can create in an easy way using tensor network states. And you know, the phases can be parameterized just by changing parameters of the tensor network. Oh yeah, many questions. So I don't know, maybe Subhro. Okay. Oh, here. Yeah. So that means that there are 2. Oh, these are multi-critical points. I can come here to 1 point from multiple phases, because the idea is a bit, I mean, maybe I should tell you the very, I mean, very roughly. Very roughly how this is going on. So you know, a wave function in 2 dimensions I can write as a as a tensor network. So this would be looking like this. So I have virtual legs which are connecting the different tensors, and then there's a physical leg. And the physical legs in my tensors I put here on these legs. And then there's a simple subclass. Not all of them are covered by that, where actually I have a condition that the physical legs are directly linked to the virtual legs of the tensor network. They're just locked by a delta function, so I can get rid of them. I can always read them off by just looking at the tensor network. And then in the end, what such a process amounts to is, let's say, a transition process from incoming legs to outgoing legs in this tensor network. This is the so-called isometry condition. And in this isometry condition, I can describe this actually by a transfer matrix of some sorts, which has a structure for the toric code, which looks like this: 1 1 0 0 1 0 1 1 0 0 1 1 0 1 0 0 1. And this would be like a 2 by 2 matrix because I have 2 incoming qubits, 2 outgoing qubits, and this is just in some notation, maybe here I have 0 0 0 1 1 0 1 1. So this just tells me that when I have 0 0, only 0 0 can enter, or 1 1 can exit, like a new vertex or nothing, right? So when I go through my circuit. And now I can parameterize this, and this condition of isometry is given by normalization of rows of this matrix. And now I can play around and modify the rows, the entries of the rows of the matrix. And when I do this, I go away from the fixed point, but create finite correlation length states. And when I tune to a point where I have an enhanced symmetry, for instance, by setting those guys to 0 here, then I will get a critical point, because here in this way, the number of loops is conserved. So this would be going from an 8-vertex model to a 6-vertex model in the language of statistical mechanics, for instance. A 6-vertex model has power law correlations in one direction. So this is the philosophy which we have, but now embedded in this framework of topological phases. And it's quite nice because we have many analytical properties for this type of states. For instance, we can efficiently sample all Pauli strings of arbitrary length, classically, even though the state has finite correlation length and very non-trivial properties. And this is very useful from a quantum information perspective because I can use them as a class of benchmark states which are highly non-trivial. Usually there's only, match gate states, which are free fermion states, or Clifford states, which are exactly solvable. But here we have another subclass of states where I can sample efficiently all Pauli strings of this tensor network. Good. Okay, so this brings this a bit into perspective. So with this perspective, we basically can understand that we can connect here all the abelian topological phases in a web represented by some tensor network, which is kind of spanning and organizing me in a space of topological order. Yes, we know everything analytically, because those phase transitions, they're typically, these are 1D, these are very anisotropic critical points, which are power law only in one direction, and in the other direction they're exponential. No, if you want to have a real 2D quantum, 2 plus 1D phase transition, then we need to go away from this simple manifold of tensor networks, which are parameterized by few parameters. We have to really go beyond that and take PEPs with a finite, at a critical point with an infinite bond dimension, because we have an infinite correlation length. And maybe I know whether Frank will cover. No, we don't. Well, I mean, in principle, yes. We also have these phases. I mean, this is a subclass of PEPs, right? So I mean, you can think of embedding these guys in this larger. I don't know how to draw this space. Even this was already complicated to draw in this larger variational space in some sense. Yes.
And the reason why you're talking about anisotropic.
No. This is 2D, completely 2D. Anisotropic comes from the fact that I have this structure in my tensor network where I have an isometry that I have a reading direction. And however, I mean, you could say, why do I restrict general tensor networks to these states? Because we know by works by Frank and Ignacio and company, we know the classification of topological order using tensor network states. But these classes of states, which I'm talking about, can be directly brought onto a quantum computer because they have the isometry constraint. Okay, so this is a subclass of states which we can implement on quantum devices directly. Whereas a general PEPS, there's no way to bring it on a quantum computer. We don't know how to do it. It's
But is it not true that
This is what we do. This is what we do. Because the correlations at the critical point, they are only in one direction, power law, but in the other direction, they're exponential. It's infinite, but the structure here in this PEPS, it has an encoded structure, a reading direction going in that way, essentially. This is the point. And this is also how we sequentially generate these circuits on a quantum computer. We start at an end and then build it up to the other end, right? So it has a reading direction. And then I can get power law correlations along the diagonal, but not, along the way I go, but not perpendicular to where I'm going. Okay. Yeah, sorry. Well, that has been solved long ago, right? To have the string net here, we want to ask, first of all, in this paper by Leo, Kirill, Adam, and Frank, they have shown that all the string net fixed points can be mapped to isometric tensor network states. So this is basically the points of the skeleton. They have shown that those can be written in that way. And now in this new paper from a couple of months ago, what we showed was that we can actually connect them in an easy way by parametrizing these circuits. Yes. Well, now, if it falls in this class of isometric tensor network states, then yes, I can directly tell you. But when you give me a generic state, this falls off the lines, right? So there is a lot of flesh around the skeleton, which we cannot describe with these isometric tensor networks directly. Yeah, I mean, this is just, I mean, you can think of this as, as your standard topological quantum field theory, which you have. The fixed points of the string nets would be like points. And then you anyway think only about those, right? When you write down field theory about coarse-grained measures. So here I'm thinking about finite correlation length states, which are broad, which are departing from the fixed point. Mm-hmm. It was?
Misnomer. Misnomer. M-I-S means N-O-M. Neither do nor.
Yeah, this is maybe, no. I mean, there's surely topological order here. It's just a lattice way of thinking about topological order, which can be very useful because I think it's very simple. That's the advantage somehow, right? So why I like this is, you just write down very simple matrices and understand everything about your topological order. You don't need any machinery in some sense, except for linear algebra to understand what is going on. So it's very simple. Yeah, another generalization would be that we can go to other forms of topological order, like the X-cube model, which was also introduced on Monday and Tuesday. So it also is of a very similar way. If you remember, the X-cube model is actually just a condensate of cuboids, or let's say a massive superposition of cuboids. So it has the same structure as a toric code almost, right? So maybe you have to be a bit more careful. And you can work out the representation of the tensor network, of this isometric tensor network, which captures this wave function. And then you can play similar games as before. You can actually ask about, I have now excitations in these systems, which are lineans and fractons. And I can now ask, how can I have this? Maybe this is one phase of meta. But then I can maybe also symmetry enrich these excitations. I can add symmetries to the problem and ask how do symmetries behave on this system. And with these tensor networks, we have very easy tools to actually do this. Because otherwise, without them, it's actually not so clear what you have to do symmetry enrichment for these fracton cases. And here we have a very clear recipe. If you're interested in this, Julian has a poster on it. Maybe you can approach him and he can explain you all the details of this. Okay, so this is the perspective why we think that this lattice perspective on topological order is very useful, actually, and can also be practically relevant. So in addition to the standard condensed matter experiments of, I don't know, fracture quantum Hall, or maybe hopefully spin liquids at some point, we have also here a way of putting these type of states on quantum processes. Okay. Yes. Stringents, yes.
So let's say I give you some group B and some cosine 2. So I give you some 2D topological order whose wave function you want to prepare on.
Yes.
What is the rest?
Well, the point what I'm making is it's going similar to the question actually what Frank has asked to Julien. We don't know on lattice, we know on lattices the string net fixed points, for instance. And this is a subclass of topologically ordered states for which you can write down all your content of your topological field theory. And those states we know how to transfer. But we don't know how to transfer, for instance, a chiral topological state yet, at least. So these are open questions. These are different questions, but the subset of, I don't say that we can transfer all topological field theories on a quantum computer, but the subclass of them, which are represented by both abelian and non-abelian string nets. That's the statement. Right.
So one can translate that fixed point.
Precisely, and this is possible because not obvious that you can write a unitary circuit which represents this wave function. This is possible. It has been shown in this part. Even less clear is it whether you can have an organizing principle where I depart. Now I know from a high energy perspective, people don't want to think about correlation lengths and those concepts. But when you approach maybe a phase transition, then you need to think about them again. And so here on the lattice perspective, we tune the correlation length from small to infinity as we approach the phase transition point. And this is precisely what we managed to do here in an analytic way. And this is remarkable, I would say. These circuits are sequential. All of them are sequential and of the same form as the toric code circuit before. And the point is, you know, the toric code fixed point I can easily prepare also in a measurement way. But these type of circuits, which have finite correlation length, in such a controlled way, I cannot. I can always put finite correlation length in some uncontrolled way by preparing the fixed point with measurement and then do a finite depth circuit. But I cannot do these controlled connections. And of course, there come deficiencies with it, like these anisotropic critical points, but also a lot of analytical understanding, I think, and this is why we like this type of states. Oh, they are non-generic, definitely, yes. Mm-hmm. No, here I just want to tell you in terms of how one can use this a bit like to use tensor network language, essentially, a simple tensor network language to walk through this phase space of topological string net states. That's all what I'm saying. Yeah. Mm-hmm. So this is a very good question. We are currently working on this a little bit to understand when you have now gates with errors, which we always have. What are the requirements actually to still get a topologically ordered state in the thermodynamic limit? It's a non-trivial question, strongly related to error correction, but this is ongoing work. I cannot fully comment on this. Good, okay. So with this perspective in mind, let's try to move on. So far I covered a simple example, let's say the equilibrium ground states and departing a little bit from the fixed point. Now I would like to study actually dynamics on top of these systems. Okay, so the idea would be to tune away from the fixed points, but in a more generic way, and also study the quasi-particle excitations and the dynamics of it on top of the state. So what we have in our mind here is again the toric code model in a longitudinal and a transverse field. But it turns out so that the toric code model is dual to the 2+1D Fradkin-Schenker model. So the 2+1D Z2 lattice gauge theory. This model is very well studied. We know the phase diagram of it since the early works by Fradkin and Schenker. So it looks a bit like this. So when I tune up here is the fixed point in the absence of any fields, is the fixed point of my toric code. When I tune up the electrical field, there will be at some point a charge confinement transition. When I tune up the gauge metacoupling, there will be, let's say, Higgs phase, right, vortex confinement. These two phases are thermodynamically connected to each other. So this is the same phase of matter, but we talk about the vortex confined and the charge confined regime, or charge and Higgs regime, if you want. I will tell you more tomorrow about how to distinguish these regimes, actually. Today, let's just keep the thermodynamic phase diagram. And here we will have the robust topological order, which is robust to some finite electric field or some finite gauge metacoupling. Right, so this is the phase diagram of this latest gauge theory. It's actually the Fradkin-Schenker model in the unitary gauge, right? So then I can drop the meta degrees of freedom, and I am left with gauge only degrees of freedom. So this is what I'm writing down here. So it's one-to-one dual. There's an isometry which connects the toric code to the Fradkin-Schenker model. Good. The question which you want to ask now is, now that we have this phase diagram, can we maybe tune the parameters in such a way that we see charge confinement dynamically somehow? And this is, of course, a very complicated problem because I have to solve a quantum many-body problem and I have to solve on top dynamics of it. Already solving the quantum many-body problem is exponentially hard and exponentially more so the dynamics in some sense, depending on your viewpoint.
So just to clarify, since this is going to be done presumably on quantum
yes.
on Google, so that means you're not really simulating.
Yes.
So then, when we talk about dynamics, you need
yes.
the knowledge of.
Yes. We will see. We will see. So first, we have to think about even to prepare a low energy state of matter. Right? We know in the toric code fixed point how to prepare the state, but we don't know when we depart from the fixed point. And this is in general a complicated problem because I want to describe a confinement transition, and to really go to the ground state is very hard. We cannot do it. But we can do an approximation of the ground state with a very simple variational state. It actually only has one variational parameter, but this is sufficient to actually, this is what the energy error per site is in the system as a function of the field. If I would take the toric code ground state as the initial state, then the energy would just shoot up as I crank up the field, because here the toric code is of course good in the topological phase, but over here it's very bad. It's not good at all. When I take the fully polarized state, which is the eigenstate of the x-polarized state, then I'm very good out here, but I'm very bad in the toric code. So I can do an interpolation here, which basically adds some imperfect rotations in my, instead of creating one plus plaquette operator, I put, let's say, relative angles between the weights of the loops. And in that way, I can create a relatively low energy state throughout the system, at least for our small system. This is, you know, in some sense a mean field. Oh, I didn't write it, right? Oh, right, but it's from you guys, a variational ansatz, which you wrote down like, well, 10 years ago now, where it's basically a mean field ansatz for my topologically ordered state. That also means that the variational parameter is just constant up to the phase transition and then it decays, because it doesn't properly build in string tension or something like this. It's just weighting loops, and this is why we call it WALA, weight adjusted loop ansatz. But for our purposes, it's enough, because we anyway have only short time evolution at our disposal. So we only need to prepare a relatively low energy state. The ground state is not needed. If you would go to long times, then you would see deviations, but these devices anyway are not coherent for long times. So we can be modest and work with this type of initial state. Yes. Right, so we do this is like a, if you want, I mean, with very fancy words, it's like a quantum classical approach. So we do the variational optimization classically, and then write the quantum circuit with this variational parameter on the quantum device, right? No, here these type of states are different compared to the ones which I showed you before. This is not of this isometric tensor network form, actually. The critical point is also different. I mean, this would be a true mean field critical point of the dual Ising model, which is dual to the toric code here. So this is not of the, this is a bit of a we can also write down an isotns, of course, corresponding to this circuit, but it's not these deformations which I was talking about here before. But this is okay. I mean, it's just. Yes. No. No, what I do is simpler. So what I do is I choose an H, for instance, this one. I prepare the variational state on the quantum device, and then I create excitations on top. And I want to see how these excitations move. This is actually my next step. And this I do for different H. And then I want to see whether the excitations are deconfined. If they are deconfined, then they would just move apart because they don't have any in time, because they don't have any potential holding them back. If they're confined, they would be more like a string sloshing back and forth. And this is the signature which we want to measure in the end, on top of these approximate ground states. Right, this is what I meant before. We choose this classically. So we classically optimize the theta and then use this as an input for my quantum algorithm to write the state. Just on a, I mean, this is a mean field state. We can do it, yeah. So we can do it in the thermodynamic limit, but we actually do it for our finite size system to have a better approximation to the ground state. So then this was actually shown here. So for finite size systems, the variational parameter look like this. You can just determine it analytically, actually. Good, okay, so that's what we want to see, confinement of charges. So they can either be deconfined or confined, depending on whether we're in the deconfined phase, the topologically ordered phase, or in the confinement regime. Okay, that's the idea. So now to the question from before. So, question? Right, this is just here. How do we do the dynamics? So now we have only prepared the state. So the dynamics we do in a very naive way. We just trotterize the Hamiltonian from before. So the e to the minus IHT, e to the minus IHT, we write as an e to the minus IH delta t with a product over n is equal to, I don't know, 1 to up to some t divided by delta t. That's true, so we have to choose it small and we have to do a clever trotter decomposition, and we did all this. There's a lot of trial and error behind that, but we can, the question is, can we make it work or not? And I mean, you can judge. So this is basically just a trotter cycle, which we have for the time evolution. And you know, it's true, we need, for each trotter step, we need 116 controlled C gates, which are entangling gates. These are a lot, even for these small systems, which we have at our disposal here. And you know, we do something like 10 layers. So these are more than 1,000 controlled C gates. So this one has to be able to do on these devices. But now once we have implemented this and done this in a, maybe not the most naive way, but thought a little bit about how to do it, then we actually see the following dynamics. So what do? So first we create an excitation. We first prepare the state. Then we create an excitation by an X flip next to each other. So this just creates two E anions. And then these E anions, because of the fields, they will undergo some motion. This is different compared to the fixed point Doric code. The E anions will move now because of the fields, right? So, and when we look at this and see, actually, when we don't have any, when we have very, very weak electric fields only, this is here. And we also have a finite, so we have a finite gauge metacoupling, and this gauge metacoupling actually makes my particles move. So when I then tune my electric field from a small value to a small value, then what I see is, as a function of time, my particles just spread. They depart from each other. When I, however, crank up the confinement field, HE, what happens is, indeed, they don't separate anymore. They stick together and even undergo a little bit of coherent motion. You know, this is this wobble picture which I showed you before, that when you are connected by springs, which is this effective simple picture of confinement here, then it would just wobble a little bit when you are initializing it in a non-equilibrium condition, and this is precisely what you see here. So the distance is more or less constant, right? So this you can see here also in the heat map, but that's not so important. So this is just, let's say, the time here and the distance measured as an average, whereas here we are directly, Okay, right. So of course, in the experiment, there's noise, and we have to take care of it. The qubits have a finite lifetime. It's a depolarization channel, which we basically mitigate and get rid of, and then we go from this to that data. Mm-hmm. Yes, let me go a bit more into the theory now. So far, we have nicely seen that there is different dynamics in the topologically ordered phase compared to the topologically trivial confined phase. Okay, so that's the statement so far. And we tune across the transition at a finite gauge meta coupling. That's very important. So it's not an Ising domain war problem, which we have, but the domain wars are addressed, right? Because we are really at finite gauge meta coupling. Whereas at zero gauge meta coupling, there would be a Kramers-Vanier duality to an Ising model, as we have seen in the Monday lectures also. Right. Let's look at this and see quality. Of course, we cannot determine critical behavior or stuff like this because this is a very small system. It's just for illustrative purposes. But at least we can uncover quite nice physics, I would say. So the point here is, let's now make a simple experiment. Let's now stay in the confinement phase. Then we have a string. And now take your favorite instrument, maybe an ukulele. We have a string and we pluck the string, okay? And now we want to see how the string vibrates in time. That's the experiment to dynamically, locally measure the excitations of the system. And this is very different and much more direct than a traditional high energy experiment would be, right? Because we literally think about what are the fundamental excitations, how can I let them ring, what are the vibrational modes, and so on and so forth, by directly creating these excitations. But of course, in a very, very small scale. But just conceptually, I think, long-term thinking, this is a different way of thinking about gauge theories. So we do this, we pluck our ukulele string and let it go. And when we are, let's say, somewhere here in the phase diagram at the start of the arrow, then basically what happens is, well, the string will just flop around up and down in my, as a ukulele string would be. But then when I go to strong confinement and I repeat this experiment, what happens is the string stays on top. It never flips down to the other side. Why is that so? Well, what is happening here is actually that the string wants to preserve its length on the top part, but it does not need to here on the left-hand side. Because you can only go to the other side by creating such an excitation of the, by changing the length on a lattice, right? So, but this would be what is known in the literature under roughening transition of the confined phase of a Z2 lattice gauge theory. So the idea is here essentially in the confinement regime, you have a transition in the types of excitations which you have. So the string can be floppy or it can be stiff depending on the choice of the confinement potential. In the stiff string, we want to keep the length of the system. Since we are on a lattice, it's Manhattan distance preserving lengths. And you know, when I make an excitation like this, an excitation like this has the same Manhattan distance as an excitation like this. This is very well known also in high energy physics and lattice gauge theories that, you know, we have the Manhattan distance which is preserved. This is why, even though in the stiff phase, the string is flopping back and forth, but only on the north. If you go to the southern hemisphere, then we need to change the length of the string. So this is not possible in the stiff phase. And this we see dynamically here in this super small experiment, but I think it's nice because it covers this, you know, from Lüscher and the Hasenfratz family from the early 80s, these predictions that there is actually a roughening transition in the confinement phase of a Z2 lattice gauge theory. So this is seen here in the dynamics. Turns out, yeah, my question. Right. Let's look at it. I want to tell you more about this actually. So the point here is, you know, this transition, what does it amount to? When you, in the absence of gauge metacoupling, which is where those people have studied this transition actually, numerically, we know an easy picture how to think about it, because it literally is just an interface problem in the dual Ising model. So we know, maybe let's do it a bit more carefully. So let's say we are now in our phase diagram, gauge metacoupling, confinement field HE, and we are at zero gauge metacoupling. then we are here out of the topologically ordered phase and in the confined phase. And I say here is somewhere my star of my roughening transition. So now when I do the duality mapping at 0 gauge metacoupling, only at 0, lambda equal to 0, then there's a Kramers-Vernier duality to the Ising model, and the Ising model is the Ising. So this is maybe lattice gauge theory. This is Ising model. Is a paramagnet here and a ferromagnet here in this side when you do the duality. So in a ferromagnet, what the domain wall amounts to is to create an interface of flipped spins. And the interface can undergo a roughening dynamics from a stiff interface to a floppy interface. This is this type of transition. But what's much nicer here is we are actually looking at it, and this is what a lot of numerics has been done in the 80s on the solid-on-solid models, Monte Carlo studies, which studied this interface problem in the Ising case. But what has not been studied, at least to my knowledge, I would be very happy to hear about this, is what happens to this interface transition actually at finite gauge metacoupling. Because at finite gauge metacoupling, it's not so clear how I write the domain wall. Because I will have dressed excitations. It's not just a simple X string, but it will be a dressed X string, which creates these excitations. And you know what Ventao, together with Ventao and Frank, what we set out to is actually to study numerically this roughening transition at finite gauge metacoupling. So to this end, again, don't give details here today, but what we do here is, here now, we don't study it in a fully two-dimensional way, but we use matrix product states, which are cylinder geometries. Previously, everything was fully two-dimensional. Now I'm thinking about putting my system on a cylinder and let the cylinder's circumference go to a very large distance. You know, why is this not a bad thing for my problem here? Because think about what we have. So the fields, what we have actually is, you know, I create an excitation and I want to see whether this excitation spreads or not. It's actually a one-dimensional quantum problem. It lives in 1 plus 1D because it's only transverse my degree of freedom which I have. But you can think of the string being fixed somewhere, right? So I lose one spatial dimension. So there will be actually very weak finite size effects in the transverse direction. So the best method, I think, to study these type of problems is actually to map them onto tensor network states. And this is what we did here. And you know now how to create a finite gauge metacoupling. This can be actually done by an algorithm which is called IDMRG. And in IDMRG, what we can do is we can first write the string in the fixed point without gauge metacoupling, and then crank up the gauge metacoupling adiabatically. And in that way, we can adiabatically create the proper string and analyze its properties. And this we did numerically here in this work, or Ventao did this numerically here in this work. And you know, the phase transition, this problem maps actually onto a compactified Sine-Gordon model. So the phase transition is of BKT type. It's of course of one-dimensional nature because it's a one-dimensional theory which we have for the excitations on top. And we know that BKT transitions are very hard to determine numerically. And the best way, at least that I'm aware of, are actually tensor network methods to do so, because we know a lot about the entanglement of conformal field theories, and we can use entanglement properties, for instance, to determine where the critical point is of my phase between a floppy and a stiff phase. And this is what we did here. So we can look at the entanglement scaling as and also at the scaling of an order parameter, which measures this. Is actually the order parameter for this transition is a translational symmetry breaking order parameter in the y direction. So if I'm in the floppy phase, I have translational symmetry, whereas in the stiff phase, I have breaking of this translational symmetry. So with this order parameter, we can then determine essentially the phase transition very accurately between these two phases, even at finite gauge metacoupling, by utilizing essentially the field theory of the compactified Sine-Gordon model in combination with quite large scale numerical tensor network techniques. Okay, and with that we can characterize even at finite gauge metacoupling this BKT transition, the roughening transition. This is here. So here's the deconfined phase. Then we go into the floppy phase, and then there's the roughening transition. And we have done simulations. So you have to be, so we have done simulations for 6 and 8 cylinder circumferences, and it's almost not moving this phase transition as we expect, because this actually are some clock models which describe these transitions, and for large enough number of entries in the clock model, you basically get just converged results for the phase transition. This is also known from different studies before. No. Here, 2 is BKT. 2 is the BKT transition of the excitation. 1 is the topological phase transition. And actually, according to my understanding, it's not even clear what happens to the floppy phase in the vicinity of the deconfinement transition. There has been a Simons Foundation program, I think hosted mainly in New York, where they try to understand what happens to strings close to the deconfinement transition. This is not solved. It's a problem which is not solved, that's my understanding at least. Right. This is very good. It connects, actually, I can tell you more tomorrow, actually, once we have introduced higher form symmetries, how it will look like. It's indeed sketched a little bit like here. So this is my phase diagram, and it will bend upwards and go asymptotically very far to the right. Why is that so? Because the roughening transition is a lattice effect. It does not exist in continuum. I need my lattice to distinguish rough from not rough. So when I go up to very large gauge metacoupling, then what happens is my length scales become larger and larger for my strings, and I don't see the lattice anymore. So the phase transition has to bend to the right. It goes like this. And I will tell you tomorrow more by introducing these notions of higher form symmetries, where they bend to, and so on. So today is a bit too much. Yes, Sergej. No, from this I have not put in the data. I mean, you need to look at the, so we can, the rough idea is, you know, when we have BKT transitions and we know the Saint-Gordon theories, we know at which Latinger parameter the lattice or the cosine term becomes relevant, and we can then actually measure operators which are charged under the Saint-Gordon theory and match the decay, power law decay of these parameters and of these correlations, and from that we actually determine the critical point. It's all written very clearly in the paper, I think, but it's technical in some sense. That you can do that very accurately. It's known for many years now that this is kind of okay. Good. Okay, very well. So that would be part 2. Now maybe it's good also for questions if you have some, and then because I think you have maybe 5 more minutes or something. Oh no, 7 minutes. It says. I can also. Yeah, the translational breaking order parameter is actually an order parameter which measures the Fourier modes in y direction. And the Fourier mode, a finite momentum Fourier mode in y direction, picks up this translational symmetry breaking. So this is how it is. E to the ikx, and you can put in any mode. We use the lowest Fourier mode, essentially, lowest finite Fourier mode to pick up this translational symmetry breaking. Mm-hmm. Yes, there's the same here. There's also the same BKT transition because we have here this would be the Latinger liquid phase of the SOS, solid on solid Ising story, and this would be the gapped phase. So this is my BKT transition from Latinger liquid to BKT, essentially. Right, but it's a bit more tricky what the compactification radius is of my theory depending on the cylinder circumference, and this we have worked out carefully. Because you need to know at which Latinger parameter do I get the transition, and this depends on the circumference because it enters in the compactification ratio radius of my conformal field theory. It's all written down in the, it's technical, it's not. This order parameter is, well, it winds around y, but in X it would be local, right? Mm-hmm. I mean, I think the effective theory is very well known. It's just a Saint-Gordon model, right? So you can do whatever you want to do with your Saint-Gordon model. It's a clock transition. You can try to do this in that way. Right, so that's nice. So when I would make a corner, then I could measure string tensions and stuff like this. We have not elaborated on this a lot. I mean, but this would be nice to actually measure string tensions and so on. Yeah, you're right. I mean, actually, we have also more data in the experimental part where some of this is discussed a little bit. I don't have it in the slides, actually. This is also a bit tricky because it's a bit like that the Wilson loops would be, you know, this is a bit tricky, right? Because here we have the confinement transition. So we basically are in the X direction. So what happens with the Wilson loops and how the dressing precisely is, this is a separate question. I don't know how precisely. This is easier than when we think more about this higher form symmetry framework, which I'm going to present tomorrow.
The question from online. Can you hear me, please?
Yes, please, of course.
Yeah, so my question is, you mentioned about this transition in this strings. So how is that going to be affected by like disorder in the couplings?
Yeah, no, this is, I do not, the short answer is I do not know.
Okay, thank you.
Good, but that's the story, you know, what I want to show you is that, you know, with these very simple, somewhat elementary tools, you can distill a lot of interesting physics about these lattice gauge theories, even though we have only very modest system sizes at our disposal. But, you know, thinking about those things, I found very useful and instructive actually to understand better topological order and their key properties. And maybe very, very briefly, I don't mention here a lot, but now, you know, we have talked about phases of matter which are in equilibrium. We can also have phases of matter which live in non-equilibrium, so out of equilibrium. One way of doing this is by using periodic modulation. When you have periodic modulation, then my time evolution operator is the time-ordered exponential like this. If the Hamiltonian comes back to itself after a period, capital T, then this unitary evolution is the same for each of these periods, from 0 to T, from T to 2T, and so on. But in between, something quite non-trivial is happening. But what one can do is actually, one can just stroboscopically look at all the times T where the Hamiltonian comes back to itself, because there we have the same unitary, and we can write it as an e to the I times T times a Hamiltonian. And this Hamiltonian is the so-called Floquet Hamiltonian. It's difficult to compute because it is extracted from the logarithm here of a time-ordered exponential. So we need to derive tools how to determine it. We can do it with a high-frequency expansion, so-called Magnus expansions, Floquet-Magnus expansions, maybe you've heard of those, from those. Or we can just think about them that we have some way of accessing these Hamiltonians. But now the point is, you know, this is like a Hamiltonian, but it's a bit of a weird Hamiltonian because it has momentum on the one side and energy is another periodic quantity because energy is only defined modulo 2 pi divided by T, the frequency of my drive, just by Fourier analysis. So the question is now, when I have such a Hamiltonian, can I create new topological states of matter, which I do not have in equilibrium? And the answer to this, I mean, people have studied this, Takuya already 15 years ago, and Mark Ratner and Nathaniel Lindner and Eresberg. They have studied this for non-interacting chiral systems, and they have actually shown, normally when you have a chiral system, the number of edge states is given by the difference of churn bands between top and bottom. So, the number of edge states, so the churn number is given by the number of edge state top minus bottom. So here we see churn number 1, and so here we would have churn number -1 if there's an edge state in between. But we can never have an edge mode when churn number is 0. However, when you have a periodic unit cell, then you can, because I can have also an edge mode going up here. And this is so-called, Floquet anomalous insulators, they call them. These are phases of matter which do not exist in equilibrium. This is non-interacting topological order. Or what I was talking about today is interacting topological order, but there we can have actually the same thing, and it's very easy. We can do a periodically modulated Kitaev model. So, you know, take the honeycomb model apply Kitaev XX, YY, CC in a periodic fashion and repeat all over again. In this way, we can actually realize a topologically ordered phase, which has, I don't go into the details because I'm running out of time. So a topologically ordered phase, which actually has Majorana excitations, has fundamental excitations, which, for instance, when you do an experiment, you can actually create Majorana excitations and exchange them, and they pick up 2 times the relative phase of e to the minus I pi over 4, which is e to the I pi over 2, which is the signature of Majorana excitations. But most importantly, there are also chiral edge states which go across the Brien zone at finite energies. So this type of topological order cannot exist in equilibrium settings, but it can exist in periodically driven systems. And we kind of also introduce a anion transmutation order parameter, which detects this phase of matter. And with that, we can basically map out a non-equilibrium phase diagram of this Fouquet topological order, where you can go from a Fouquet topological phase at fast drive frequencies to actually also a very exotic phase at low drive frequencies, which is the non-abelian Kitaev phase here. So this is a phase transition which is realized, let's say, transiently in these quantum devices in that way. Okay, good. But with that, let me just flash the summary. So I wanted to show you some examples of how we can study hands-on states with topological order on quantum devices, ranging from toric code, excitations of toric code, to maybe something more exotic like this Fouquet topological.
Okay, now let's thank Michael.
I guess there were many questions already.
Yeah, there were many questions during the talk.